Okay, today's topic is dividing with polynomials. So last time we talked about what polynomials were. We talked about adding and subtracting and multiplying polynomials. This time we are going to be dividing polynomials, but we're going to start off with a little bit of a review. So a proper fraction, we've seen this before, but a proper fraction is a fraction where the numerator is less than the denominator. So like 3/8 is a proper fraction because 3 is less than 8. An improper fraction is a fraction where the numerator is greater than the denominator. So 8/3 would be an improper fraction. And anytime you have an improper fraction, you can always choose to represent that as a mixed number. And a mixed number is an integer plus a proper fraction. Like 8/3 could be 2 plus 2/3. That's an integer plus a proper fraction. If I wanted to write 13/4 as a mixed number, what would that mixed number be? Three plus 1/4. And if I wanted to write 3 plus 2/5 as an improper fraction, that would be 17/5. And we next talked about long division. We said long division is a method for rewriting improper fractions as mixed numbers. And we do this if we can't tell just by looking at it what mixed number this is going to end up being. So we want to divide 1,613 by 7. And we say, how many times does 7 go into 1? 0 times. How many times does 7 go into 16? 2 times. So 2 times 7 is 14. 16 minus 14 is 2. We bring down the 1. How many times does 7 go into 21? 3 times. And 3 times 7 is 21. That's 0. We bring down the 3. And then how many times does 7 go into 3? 0 times. And 3 then is my remainder. So we called this number up top, we called it the quotient. We called this number down here the remainder. And the way we wrote our answers is we took this numerator over denominator and we write it as quotient plus remainder over divisor. So this answer is saying 1,613 divided by 7 is equal to 230 plus 3/7. And so with long division, we keep going until the remainder is less than the denominator. So that way, whenever I write my answer, I've got a proper fraction there at the end. Okay, one more, and then we'll move on to other stuff. So if I wanted to divide 748 divided by 34, how many times does 34 go into 74? 2 times. And 2 times 34 is 68. 74 minus 68 is 6. Bring down the 8. And then, of course, once again, 2 times 34 is 68. And so this time my remainder is 0. And the important part that I want you to see this time is that I can write 748 divided by 34 is equal to 22, that's my quotient, plus 0, that's my remainder, over my denominator. But 0 divided by 34 is just 0, and I don't have to write plus 0. I can just write that instead. And this equation, if I take this equation and I multiply both sides times 34, I get 748 748 is equal to 22 times 34. That tells me that 34 is a factor of 748. And this is always true. If my remainder is 0, then the denominator is a factor of the numerator. And if the remainder is not 0, then you can't say that. You can't say that the denominator is a factor of the numerator. It's only a special case. If you do division and you get a remainder of 0, then you know the denominator is actually a factor of your numerator for that reason. So to recap, we can only do long division to an improper fraction, because if you have a proper fraction, there's no reason to do long division. Long division stops when the remainder is less than the denominator. That's how we'll end up with a proper fraction at the end. When the remainder is not 0, the denominator is not a factor of the numerator. And when the remainder is 0, the denominator is a factor of the numerator. And in the end, we write n over d equals q plus r over d. Now, new material for today. We're going to be dividing polynomials. And this exercise says divide these polynomials by factoring. I'll show you what I mean. I've got the polynomial x squared minus 3x minus 10 divided by the polynomial 2x minus 10. And I'm going to factor the top and factor the bottom. And that's what I mean by factoring. And the numerator factors as what?
X minus 5 and x plus 2.
Very good. X minus 5 times x plus 2. And the denominator factors as 2 times x minus 5. So here, I notice a common factor between my numerator and my denominator. So I can simplify just by canceling out that common factor. And after canceling, I get x plus 2 divided by 2. And this is a linear polynomial with the expanded form 1/2 x plus 1. So that's my answer. And that's what I mean if I say divide by factoring. I mean factor the top, factor the bottom, cancel out any common factors, and then simplify.
For example, if we didn't simplify the bottom one and got, instead of getting left with the 2, if, let's say it's just x minus 5, they cancel out, you are left with 1. So it would be like x plus 2 over 1.
You can't get x plus 2 over 1.
I'm saying if there wasn't, like if it was just x minus 5.
Oh, okay. You're saying if the 2 wasn't here,
Yeah.
then you're right. It would just be x plus 2. Yeah. Okay. Let's do another example of that. Again, we're going to divide by factoring. This time, my numerator is just one factor, right? It's already factored. My denominator has these 3 terms, and there's actually a common factor between those 3 coefficients. So 3, 21, and 36, those are all divisible by 3. And so if I take out that common factor, I get x squared minus 7x plus 12. And so this is going to be 3 times something.
X minus 1, x minus 2.
Yeah. Just like that. And once again, just like before, I'm going to cancel out the common factor that I have in the numerator and denominator. And this would become 1 over 3x minus 9. I went ahead and I expanded by distributing this 3 to the x and distributing the 3 to the negative 3. So you factor the top, factor the bottom, cancel the common factors, and simplify. Any questions? Okay. So next, if we use the term rational function, a rational function is a ratio of two polynomials. So this is a rational function if we say n is a polynomial and d is a polynomial. Then n divided by d is one polynomial divided by another. That would be a rational function. A proper rational function is very much like having a proper fraction. A proper rational function is one where the degree of the numerator is less than the degree of the denominator. And whenever we were talking about proper fractions, we said a proper fraction is one where the numerator is less than the denominator. Because with numbers, we could just compare the numbers. With polynomials, it doesn't really make sense to say that one polynomial is bigger or smaller than a different polynomial. So instead, we just compare the degree of the polynomials. And we say it's proper if the numerator has a smaller degree than the denominator. So an example of a proper, rational function might be something like 2x plus 5 divided by x squared minus 1. Because the degree in the numerator is 1, and the degree in the denominator is 2, and 1 is less than 2. So that makes it proper. On the other hand, an improper rational function is one in which the degree of the numerator is greater than or equal to the degree of the denominator. And that's important. It's not just greater than, but it's greater than or equal to. And that means there's two ways you might see this. You might see a situation where you have like x cubed plus 5 divided by x squared. Here, 3, my degree of my numerator, is greater than or equal to 2, the degree of the denominator. But another thing you might see is just like x squared minus 1 divided by x squared. And the degree of the numerator is 2, and the degree of the denominator is 2, but we still call this improper if they're the same degree. Now this should sound a little bit familiar, like in analogy to fractions, right? Any improper rational function can be expressed in a mixed form. Just like an improper fraction can be represented as a mixed number, where a mixed number is an integer plus a proper fraction, an improper rational function can be expressed in what we call mixed form, and that's just a polynomial plus a proper rational function. So, examples. If I take this orange improper rational function, I could rewrite this as x cubed divided by x squared, which is x, plus 5 over x squared. And that is a polynomial plus a proper rational function. And this one right here, that's also an improper rational function, I could represent that as 1 minus 1 over x squared. And again, that's a polynomial plus an improper rational function. Or sorry, I misspoke there. That's a polynomial plus a proper rational function. 1, the number 1 is a polynomial. It's a boring degree 0 polynomial, but numbers still count. Any questions so far? No? Okay. So we'll do a bunch of examples now. If I say rewrite this improper rational function in mixed form, you can see this is improper because the degree of the numerator is 1 and the degree of the denominator is 1. What I'm going to do is rewrite it x plus 8 over x minus 3. But then I'm going to do a little trick. I'm going to do x minus 3 plus 3 plus 8. And then I can go ahead and split up this fraction anywhere where I see a plus sign or a minus sign in the numerator. So like I have like x minus 3 plus 8. I'm allowed to go ahead and just split that fraction at that plus sign if I want to. You just have to keep the same denominator. And the reason for doing this is because the first fraction is just the number 1. Yeah. If I've got x minus 3 divided by itself, that's just 1. And then this part is 3 plus 8 divided by x minus 3. And so now I've got a polynomial plus a proper fraction. This is what we call mixed form. So I'm allowed to do minus 3 plus 3 because that just cancels out. That's like adding 0. I can add 0 and it doesn't change the value of my expression. And the reason I want to do that is because I want the first part of the numerator to look exactly like the denominator. I want to see x minus 3. Because if I do that, then I can separate my fraction, and x minus 3 over x minus 3 just gives me a 1. So that was the whole strategy all along. We'll do one more like that. So here, my improper rational function is x squared plus 1 over x squared minus 3x. So what should I add or subtract in the middle here to do the same trick? Yeah, I'm going to go ahead and do x squared minus 3x, because that way the first part of my numerator looks just like my denominator. But then in order to not change the value of this expression, I also have to add 3x. And that keeps everything fair and balanced here. And at this point, I can imagine splitting this fraction, right, where that plus sign is, the orange plus sign. And then the first fraction would look like x squared minus 3x divided by x squared minus 3x. And that's just the number 1. And then the second part of this numerator is 3x plus 1. And the denominator is still x squared minus 3x. And so this is my mixed form. This is something you can do anytime the degree in the numerator is the same as the degree in the denominator. So in this case, both were 2 on the top and 2 on the bottom. In the previous example, it was degree 1 on the top and degree 1 on the bottom. That's how you know you can actually use this little trick to get the mixed form. We'll talk about other strategies for when that's not the case, because you might have a higher degree in the numerator. But first, we'll think about the opposite direction. What if I want to rewrite this improper rational function in expanded form? So this time, it's actually given to us in mixed form. And I want to expand this. And so if I have 2 plus 1 over x plus 3, what I need to do here is find a common denominator. And that means 2 is the same thing as 2 over 1, and I can multiply this by x plus 3 over x plus 3, because that's like multiplying times 1. Doesn't change the value of my 2 right here. But I might want to do that because now I can write 2 times x plus 3 plus 1 divided by my common denominator. And now the denominator is just x plus 3. And then the last step is just to distribute the 2 and collect your constant terms. So I'd end up with 2x plus 6 plus 1, or 2x plus 7 divided by x plus 3. And that would be the expanded form we're looking for. Taking a pause for any questions, concerns? No? It's still super clear? Okay. That's good. So let's do another one. And this one's going to be a long problem. It's long, but it's not too difficult. Once again, I get a rational function, and this is, honestly, it's not in expanded form, and it's not in mixed form either. This is a different thing altogether. And we won't talk about this too much in class. And this is the last time you'll even hear me say this, but this is called decomposed form. And you don't really need to know about this. All you need to know is that we want to put it in expanded form. And what we would do to put this in expanded form is we would write 2 plus 1 over x minus 1 plus 6 over x plus 3. And then, just like before, we're going to find a common denominator. It's tougher now because I actually have 2 different denominators and 3 different terms. And so this one gets a little bit trickier. Like, to get this 2 to have the same denominator as the other 2 terms, I have to multiply by x minus 1 over x minus 1. And I also have to multiply by x plus 3 over x plus 3. For the middle term, I only have to multiply by x plus 3 over x plus 3. Because I already have the x minus 1. in my denominator for the middle term. And then for the last term, I only have to multiply by x minus 1 over x minus 1. Because once again, I already have the x plus 3 in that denominator. And once I'm done here, I should have a common denominator. It's not difficult, it's just long. And the common denominator we're going to end up with is going to be x minus 1 times x plus 3. That's x squared plus 2x plus 3. Now, in the numerator, I have to do 2 times x minus 1 times x plus 3. But that's just 2 times what I just wrote in the denominator, right? I've already multiplied those two things before. I don't have to do it again. And so I'll do 2 times x squared plus 4x plus 6. That's that first part. And then I'll go ahead and switch colors for the second part. This is just plus x plus 3. And then the last part is plus 6x minus 6. And the last step here is to simplify. I'm just going to collect like terms. There's only one term with an x squared, so I keep the 2x squared part. For my x terms, I've got 4x plus 1x plus 6x, that's plus 11x. And then the constants are 6, negative 6, and 3, so plus 3. And that is expanded form. So once again, this type of problem that you have in exercise 4 is not hard. It's just sometimes long. Sometimes finding a common denominator takes a little bit of work. And you just have to be really careful not to make any silly little mistakes with your plus signs, your minus signs, and distributing stuff, because it could be easy to make a mistake. So here's my advice if you're working through the homework. Whenever you work through exercise 4 of the homework, and you want to check your answer and make sure you got it correct, you should go to my favorite website and type in what you got for your answer. So our answer was 2x squared plus 11x plus 3. And then in the denominator, x squared plus 2x plus 3. And that is what that function looks like. At least what we found for my answer. And this is how we check our answer. We go back to what we were originally given, which is 2 plus 1 over x minus 1. Plus 6 over x plus 3. And look, if they are not the same graph exactly, that means we made a little mistake somewhere, right? This is how you use Desmos to check your work. If they were actually the correct answer, then the blue curve and the red curve should be exactly the same curve. It should be the same function. And whenever I check my answer and I see that I got something like this, where they don't match, that's telling me, something is up. I clearly made a mistake somewhere. Now I just have to figure out where I made my little mistake along the way. So, who can tell me where my little mistake is?
It should be -3 on the bottom.
Thank you. Yeah. When I multiplied x minus 1 times x plus 3, the -1 and the positive 3 should give me a -3 for my constant here. And another place where I used that is whenever I said, okay, well, in the first term, 2 times that is just 2 times the denominator. So I really need to make this a -6 as well in the numerator, like that. Now, if it's -6 plus 3 minus 6, that's -9 for my constant in the numerator, and -3 for your constant in the denominator. And now let's check and see if that does the trick. Maybe we found the only mistake, maybe not. Okay. So if you get the correct answer in Desmos, this is what it should actually look like, right? The red curve is exactly the same as the blue curve because these are really the same function, just written 2 different ways. And that's how you check your answer on like homework questions, right? Desmos is really helpful for that. Okay, so this is the main event for today. It's called polynomial long division. And this is a method that we use for rewriting an improper rational function in mixed form. So here is an example where I have an improper rational function, and I want to write this in mixed form. And I got 2x cubed plus 6x squared plus 3. And I've got an x to the power 3, I've got an x to the power 2, and I've got a constant term. I actually don't have a linear term. Like I don't have an x to the power 1 term. And this always helps me. What I'm going to do is actually write in plus 0x plus 3. And that 0x is going to serve as a little placeholder. And it's going to remind me that there should be an x term there. And it's going to help me avoid making any silly mistakes. So I highly recommend that. Whenever you're doing long division, just go ahead and throw in a 0 as a coefficient if you happen to be missing any of the terms. And then we want to divide by x plus 5, and this is how it works. I look at my first term in my denominator and the first term in my numerator, and then I ask, what times x gives me 2x cubed? 2x squared. Awesome. Yeah, so 2x squared times x gives me 2x cubed. And I also have to multiply 2x squared times 5, which is going to give me 10x squared. And then we're going to put parentheses around this, and we're going to subtract it. And to me, the parentheses are important because it reminds me that I'm subtracting 2x cubed minus 2x cubed, but I'm also subtracting 6x squared minus 10x squared, which is negative 4x squared. And if I don't put down the parentheses, sometimes I can make the mistake of accidentally doing 6x squared plus 10x squared and getting 16x squared, but that would be wrong. That's a common tripping up point, right? That's a common stumbling block. So try to avoid that. And again, the parentheses, that helps me remember I'm subtracting these things. And then I want to bring down the plus 0x and the plus 3. And the next question I ask is, what times x gives me negative 4x squared? And the answer is negative 4x. Yep. So negative 4x times x gives me the negative 4x squared. And I also have to multiply negative 4x times 5 for a negative 20x. And then I put parentheses around that and I subtract. And I've got negative 4x squared minus negative 4x squared, that's 0. 0 minus negative 20 is positive 20x. And I bring down the 3. Two negatives make a positive. So 0 minus negative 20 is 0 plus 20. Yeah, good question. Okay, and the last time I do this, the last question I'm going to ask is, what times x gives me 20x? So 20 times x is 20x. Also, 20 times 5 is 100. And then remember to put parentheses around this and subtract. And then 20 minus 20 is 0. 3 minus 100 is negative 97. This is where we stop. And you could imagine saying, what times x gives me negative 97? And there's an answer to that. It's actually negative 97 divided by x times x gives you negative 97. But we're not going to go down that road. We're just going to stop. We're going to stop whenever our remainder has a degree that's less than the denominator. This time my remainder has a degree of 0, and my denominator has a degree of 1. And since 0 is less than 1, that's why we're going to stop. I'm choosing that specifically as a cutoff point because I'm trying to write a polynomial plus a proper rational function. And in a proper rational function, I just need the remainder to have a degree smaller than the denominator. Just like before with long division, the goal is that I have some numerator divided by some denominator, and I'm going to rewrite this as a quotient plus a remainder divided by that same denominator. Only I want this to be a mixed form. So I want q to be a polynomial, and I want r divided by d to be a proper rational function. So this is my remainder. This up here is my quotient polynomial. And I'm ready to write my answer down. I can write 2x cubed plus 6x squared plus 3 divided by x plus 5 is equal to 2x squared minus 4x plus 20 minus 97 divided by x plus 5. And this is what we call the mixed form because it is a polynomial plus a proper rational function. That's how we use polynomial long division to take an improper rational function, like we started with, and rewrite it as a mixed form, which is a quotient polynomial plus a remainder over the denominator we started with. Any questions about that process? I do have more examples to show. And so if you felt like you didn't 100% catch what was going on, maybe more examples will help. And here's our next example. We've got, rewrite this in mixed form. And again, this is an improper rational function. So I can write 3x squared plus 6x plus 3 divided by x squared minus 9. So the first question we should ask is, what times x squared is going to give me 3x squared? 3. So 3 times x squared is going to give me 3x squared. And just by the way, sometimes to keep track of my work, I like to throw in the missing terms, right? Like 0x. And that reminds me that really I should leave a little placeholder for that. I should multiply 3 times 0x, and that would just be 0x. And then finally, 3 times negative 9 is negative 27. And we use our parentheses and we subtract. And 6x minus 0x is still 6x. And 3 minus negative 27 is plus 30. And we stop. I know that I'm supposed to stop because the degree of my remainder is less than the degree of my denominator. The remainder has degree 1, but the denominator has a degree of 2, so I can stop right here. And I write my answer using that old formula, quotient plus remainder over denominator. So I write 3 plus 6x plus 30 divided by x squared minus 9. So this is a mixed form where my polynomial is 3, and then my proper rational function is also right there. Questions about that one? All right, one more of these before we move on. So this is our last polynomial division example. I've got 2x cubed minus 5x squared plus 2x minus 5. And I'm going to divide by x squared plus 0x plus 1. And we ask, what times x squared gives me 2x cubed? 2x, yeah. 2x times x squared is 2x cubed. 2x times 0x is plus 0x squared. And then 2x times 1 is just plus 2x. Put down the parentheses and then subtract. So 2x cubed minus 2x cubed is 0. Negative 5x squared minus 0 is still negative 5x squared. 2x minus 2x is 0x. And then I bring down this negative 5 at the end. Okay? Now we ask, what times x squared gives me negative 5x squared? Negative 5. So negative 5 times x squared gives me negative 5x squared. Negative 5 times 0x is still plus 0x. And then negative 5 times 1 is negative 5. So I put parentheses around this, and I subtract. And I'm subtracting the same thing, so I get 0. That means I can go to write my answer. And I can say that this, numerator over denominator equals quotient plus remainder over denominator. Well, here's my quotient. This is my remainder. And I can write my answer like 2x minus 5 plus 0 over x squared plus 1. But 0 divided by x squared plus 1 is always 0. And I don't have to write plus 0. So I don't have to write that little last part. And if I take this equation right here, and I go ahead and I multiply both sides of the equation by x squared plus 1, then I can rewrite this equation like 2x cubed minus 5x squared plus 2x minus 5 is equal to 2x minus 5 times x squared plus 1. And that means that this x squared plus 1, that's a factor of my cubic polynomial in the numerator. And this is always true. So I'll write out what we're trying to say. Whenever my remainder is 0, this means my denominator is a factor of my numerator. And when the remainder is not 0, then the denominator is not a factor of the numerator. Does that make sense? Any questions? Okay. So a little recap. We can only do long division to an improper rational function. If you already have a proper rational function, there's no reason to do long division. Long division is going to stop only when the degree of the remainder is less than the degree of the denominator. The remainder is not 0 whenever the denominator is not a factor of the numerator. And the remainder is 0 when the denominator is a factor of the numerator. And the last thing that I haven't actually said before, that you should pay a little bit of attention to, is that the degree of your quotient polynomial is equal to the degree of your numerator polynomial minus the degree of your denominator polynomial. So if we're only talking about degrees, you take the numerator minus the denominator, and that equals the quotient, just for degree. And I have 3 examples to show you that this works. Let me show you my 3 examples. In this one, the degree of the numerator is 3. The degree of the denominator is 1. So 3 minus 1 is 2. And the degree of my quotient is 2. Okay, next one. The degree of my numerator is 2. The degree of my denominator is 2. So the degree of my quotient is 0. 2 minus 2 is 0. And then the degree of my numerator is 3. The degree of my denominator is 2. So 3 minus 2 is 1. And my quotient has a degree of 1. But that will always work. All right, let's talk synthetic division. Synthetic division is a shorthand for long division. Really quickly, remember for a second, when we wrote an augmented matrix, the augmented matrix was just a shorthand representation for a system of equations, right? We were basically writing the system of equations, but we didn't write the x's, and we didn't write the y's, and we didn't write the plus signs, and we didn't write the equal signs. We're going to do the same thing with synthetic division. I'm going to write this division problem down, only I'm not going to write the x's. I'm not going to write x squared or x cubed. I'm not going to write the plus signs. I'm only going to be interested in writing down a few numbers, and that's still going to capture the whole idea, and we'll still be able to work the problem. I just don't have to write nearly as much. So this is the way it looks. I draw a little box, and I draw a line, and I draw another little box. And then this -5, I wrote -5 in the box because this is the root of the denominator. It's a common mistake for students to write +5 in that box, because when you look at the denominator, you see x plus 5, but you have to think to yourself, I actually want the root, and the root of x plus 5 is actually -5. Then I wrote 2603 across the top, because those are the coefficients of my numerator. And I also, this time, I don't have an option. I have to write the 0. And the reason I have to write the 0 is to represent the term that looks like plus 0x. And I don't normally write plus 0x. But this method of synthetic division won't work unless you remember to include the 0 placeholders. Okay? And now we've set up the problem, I'll show you how to solve. We start by bringing down this 2. And so I say I bring down the 2. And then I'm going to multiply. Multiply 2 times -5 in the box. And 2 times -5 is -10. Now we're going to add vertically. We're going to add 6 plus -10, and that would be -4. And then we multiply again. I say -4 times -5 is +20. And we add vertically again. So I say 0 plus 20 is 20. I'm going to multiply again. 20 times -5 is -100. And I'm going to add vertically again. 3 plus -100 is -97. Okay, so we've solved the problem. We just have to now interpret what is my solution. And this is how you tell what the heck your solution is. The number in the box is my remainder. Next to that, this is going to be my constant term for my quotient polynomial. Next to that, that's going to be the x coefficient for my quotient polynomial. And next to that, this is going to be my x squared coefficient in my quotient polynomial. So when I go to write my answer, I can write 2x cubed plus 6x squared plus 3 divided by x plus 5 is equal to 2x squared minus 4x plus 20 minus 97 over x plus 5. And now you can see on the right the mixed form. Remember, this is just n over d equals q plus r over d. Are there any questions about how we do this? If I ask you to do synthetic division again?
So is the two, like, or whatever numbers there, it's just going to go straight down and then you multiply?
The first one goes just straight down.
Okay.
And then you start to multiply and then add, and then multiply and then add, and then multiply and then add, and then, yeah. Good question. So we've actually already done this problem. This was the first problem we did with polynomial long division. And I'll scroll up to that, and you can look at it. But we got the same answer right here by doing polynomial long division. But we had to write down some more symbols, right? We wrote the x's every time, we wrote the parentheses, we wrote the minus signs and the plus signs and the arrows and the bars and whatever. And what I want to point out is that if you look at these numbers, like -2, -10, +4, +20, -20, -100, -97, all of that should look really familiar to you because we just found all of those numbers all throughout here. We're doing the same exact math with the same numbers. This is just a shorthand. It just means you don't have to write as much to do it. Okay? And we'll do one more example of this and then we'll move on. But here we have division problem. What goes in the little box? -2, because that's the root of the denominator. And then across the top, I write 1, -1, -1, 0, and 7. Because those are the coefficients in my numerator. And we're ready to solve. I just have to bring down the 1. 1 times -2 is -2. Plus -1 is -3. Times -2 is +6. Plus -1 is 5. Times -2 is -10, plus 0 is -10, times -2 is +20, plus 7 is 27. And 27 is my remainder. -10 is going to be the constant term of my quotient. 5 is going to be the x term of my quotient. -3 is going to be the x squared term of my quotient. And then this 1 is going to be the x cubed term of my quotient. So when I go to write my answer, I write 1x cubed minus 3x squared plus 5x minus 10 plus 27 over x plus 2. It's way faster than doing polynomial long division. No, that's a good question. It is not possible if the denominator is squared. And that was a great segue into my next statement here. We can only use synthetic division if the denominator is linear and monic. On the other hand, polynomial long division always works. So there may be a situation on your homework and on your tests where you have to use polynomial long division and you can't use synthetic division. Because polynomial long division, it takes longer, but it always works. The downside to synthetic division is it only works in the case where your denominator looks like this, right? It's x plus or minus some constant. Because if you have anything in front of the x, like you got 2x plus 3, sorry, the 2 makes it not monic. And it has to be monic. If you had x squared plus 3, well, too bad. X squared means it's not linear, and so it's not going to work. And so if your denominator is squared, then you would have something non-linear in the denominator, and so that wouldn't work. Just to really drive the point home, is this appropriate for using synthetic division? No, because the denominator is not linear. Is this appropriate for synthetic division? No, because the denominator is not monic. You can't have that 3. Is this appropriate? Yes. So for these first two questions, you would have to use polynomial long division. For this third one, you could actually use synthetic division, and it would be fine. Okay, this is a very magical piece of math that should sound absolutely insane the first time you see it. It's called synthetic substitution, and this is how you use synthetic substitution. We want to evaluate this polynomial. So I have a polynomial, and it is y equals x to the 5th minus x to the 4th plus 3x cubed minus 2x squared plus 3x minus 3. And I want to evaluate this at the point x equals 2. And the way that we evaluate functions is we just go through the function, and everywhere I see an x, I'm going to replace that with a 2. So it's 2 to the 5th minus 2 to the 4th plus 3 times 2 cubed minus 2 times 2 squared plus 3 times 2 minus 3. Okay? But there's an alternative. The alternative is called synthetic substitution, and this is how it works. We're going to draw a little box and another line and another little box. And then in the box, I put 2 because x is equal to 2. And then across the top, I'm going to write 1, negative 1, 3, negative 2, 3, negative 3, because those are the coefficients of my polynomial. And I'm going to go along and just pretend like I'm working a synthetic division problem. So I bring down the 1. 1 times 2 is 2, plus negative 1 is 1, times 2 is 2, plus 3 is 5, times 2 is 10, plus negative 2 is 8, times 2 is 16, plus 3 is 19, times 2 is 38, plus negative 3 is 35. And now, my answer for evaluating the function is y equals 35. It's whatever ends up in that box. And the first time I saw that, I thought, that's crazy. There's no way that works, right? Like, that sounds crazy. That sounds made up. Doesn't seem like it should work. The regular way, when we do things, like normal, we would say, I have to know what 2 to the 5th power is. That's kind of a drawback if you don't have your powers of 2 memorized. But if you do know your powers of 2, that's 32 minus 16 plus 3 times 8. 3 times 8 is 24, minus 2 times 4, which is 8, plus 3 times 2, which is 6, minus 3. And then 32 minus 16 is 16. 16 plus 24 is 40. 40 minus 8 is 32. 32 plus 6 is 38. And 38 minus 3 is 35. And then, the first time I saw this, I thought, okay, well, that's just a coincidence. Like, maybe you can find that for some polynomials, but surely it can't work for all of them, right? It's crazy. But it does. This definitely works for every single polynomial. And I'll tell you why this always, always works. The explanation is called remainder theorem. And the remainder theorem states, let's say capital P represents any polynomial, right? This should work for all polynomials, not just 1 or 2. So capital P is any polynomial, and C is any constant number. When we use the polynomial long division algorithm, and the polynomial long division algorithm takes some numerator divided by some denominator, and it produces a quotient plus a remainder over a denominator, same denominator. When we use that polynomial long division algorithm to find the remainder of this, P divided by x minus C, then this remainder is always a constant, and it's always equal to this polynomial evaluated at the point where x is equal to c. Okay? What's the proof? Right? How do we know this always, always works? So long division says this is equal to some quotient plus remainder over x minus c. Okay? I'm going to take this equation and I'm going to multiply both sides of the equation times x minus c. So on the left side, it cancels and I just get p. On the right side, I get q times x minus c plus r. So when I multiply times x minus c, it's going to cancel out that one too. Okay? So now I've got a formula for my polynomial. And the next step here is to say, I want to evaluate this polynomial for x equals that constant c. And that means I take my formula for this polynomial, and this time I replace the x's with a c everywhere I see an x. And this c minus c is just 0. So that means p is equal to q times 0. So that whole part is just 0 plus my remainder. In other words, my polynomial is equal to my remainder when I evaluate at the point x equals c. The only thing I haven't said explicitly is how do we know that this remainder is for sure a constant, like just a number? The remainder is not a polynomial. We know the remainder has to be a constant because long division keeps going until the remainder has a degree smaller than the denominator. But this time my denominator has a degree of 1, so my remainder has to have a degree smaller than 1. In other words, my remainder has to have a degree of 0 and that means my remainder is a constant. So, just to recap, if I use long division to find the remainder of this, then the remainder is equal to that polynomial evaluated at this point, the minus c part. So, when I go to do this, the synthetic substitution stuff, setting this up looks like synthetic division if I were going to divide this polynomial by x minus 2, right? Because I put the root of the denominator there. And then my remainder theorem says, well, if I do p divided by x minus 2, the remainder that I get, which always ends up in that bottom box, is going to be equal to my polynomial evaluated at 2. And that's why synthetic substitution actually works. And we know it works for every polynomial. So we're almost done. We'll just do one more example. And then we'll head home. I'm going to do synthetic substitution. I want to evaluate this polynomial at the point x equals 3. So I put a 3 in the little box. Across the top, I'm going to write 2, -2, 0, -1, 1, and -10. And this is how we solve. You bring down the 2. 2 times 3 is 6. 6 plus -2 is 4. 4 times 3 is 12. Plus 0 is 12. 12 times 3 is 36. 36 minus 1 is 35. 35 times 3 is 105. 105 plus 1 is 106. 106 times 3 is 318, and then 318 minus 10 is 308. So this polynomial, if I evaluate at x equals 3, is 308 in value. And again, the big benefit of this method is that I don't have to know what is 3 to the 5th power. I don't have to worry about that.